Okay, so we're going to continue on where we left off last time, and that is going to be here in section 10.8, spur gear selection. So if you are following along in your textbook, this is going to start on page 275. Now, when we're specifying gears, all right, and we've kind of touched on this and talked about this as we've gone along, we know that we have to specify for each individual gear three things. We need to specify the diametral pitch. That's going to be our capital P with a sub D at the end of it. We need to specify our pressure angle, and we also need to specify the number of teeth in each one of the gears that are going to be in mesh with one another. So as we look here on our next slide, talk a little bit about diametral pitch again. If you recall, diametral pitch is the size of the tooth. If you need to, kind of be reminded, there are two terms in our vocabulary for gears that sound very similar. The first one is a diametral pitch. See, let me go underneath here. Diametral pitch. Diametral pitch, which is what we're talking about now, is literally the size of the tooth, and it's given as a number. There are units associated with this. We know it to be teeth per inch, but we never like give it or get it with the value of units in back of it. So we basically, if somebody specifies a number 5 gear, that's its diametral pitch. And that means that this, in kind of, perspective is going to be the size of the tooth. Okay. If it's a larger number, so notice that our small numbers are down here at the bottom where we have the larger, bigger, chunkier teeth. And our very largest numbers, our highest numbers are going to be at the top where we have the smaller teeth. Okay. When you think about this, that equation is going to be the number of teeth per inch of pitch diameter. So it's not, if we measure along the circumference an inch, how many teeth would be in there. That is not what it is. It's per unit of straight line across the diameter. So it kind of makes sense that the higher the number, the smaller the teeth. It's like more teeth that we can fit in that unit of measure. Okay. So that's diametral pitch, the size of the tooth. The other term that sounds very similar is pitch diameter. And I wanted to show you that one illustration that I like. Pitch diameter is going to be different. It is the physical size of the tooth, or physical size of what I like to call the effective diameter. Okay. So as we look here, the pitch diameter is going to be between the top of the tooth and its root, not at the halfway point. Remember, addendum and dedendum are actually different numbers, but that pitch diameter is going to be, I got it out of focus. There we go. It's going to be what is going to be in tangent with whatever gear that is in mesh with. So you'll notice that the teeth overlap here, and where their tangent is going to be on their pitch diameters. Okay. So it's going to be this diameter is the pitch diameter of the gear on the right. And this is the pitch diameter of the gear on the left. Okay. So it's not the outermost, it's not the down below on the root of the tooth. It's kind of like in between. I'm not going to say halfway because it's not, but it is in between. And it's where you have those teeth actually physically engage with one another. Okay. So pitch diameter is this. So diametral pitch, it's going to be the size of the tooth. And that's going to be the first thing that we identify when we're specifying a gear. What is the size of that tooth? Any two gears that are in mesh with one another have to have the same diametral pitch, have to have the same size tooth. Okay. So, looked at that. Now on table 10.6, this is on page 275 at the bottom on the right-hand side, table 10.6. This is going to give us a way that we have a place to start with what is the right size diametral pitch we should be worrying about. Now this particular table is specifically for mild steel gears that have a 20-degree pressure angle. Okay. So if I go underneath here, table 10.6, okay, this is suitable diametral pitches for 20-degree mild steel, which is a vast majority of the gears that we engage with, especially in industrial settings. So how we size this is we look at the pair of gears and we find out which one is the higher speed of the two. Okay, meaning usually it's going to be the pinion. The smaller gear is going to be rotating at a faster rate than the larger gear that's going to be in mesh with one another or engaging with one another. So we pick the higher speed of the two. And then we find out how much horsepower are we pushing through that set of gears, okay? So the first column is going to be the horsepower for the application. And then the columns going across the top are going to be our rotational speed of, like I said, it says here the pinion, but it's going to be the one that's going faster. Sometimes that can be the gear, I don't know, but the pinion speed. So for instance, if we have an application, we've got 1800 RPM and our horsepower is at 1 horsepower that we're pushing through, we find where those two come together. And in this case, they're suggesting you start with a diametral pitch of 20 for your application. If you have something that's going slower and you're pushing more horsepower through, notice that that number gets larger, okay? As the number gets larger, as the number gets smaller, the teeth get larger. So I said that wrong. So up here we had 20s, down here we have 8s and 6s. That means as we move down this chart, we're pushing more horsepower through. We need bigger, chunkier teeth. So the numbers are getting smaller, okay? Remember, the smaller the number, the larger the tooth, okay? So this chart is really just to get us in the ballpark. It's where do we start, okay, with the size of the tooth. And again, that's going to be your pinion speed, or the faster of the two that are engaged, and the horsepower that we have for this application. The pressure angle, as we know, there are 3 pressure angles here. We've already talked at length about this and how those components of that force affect things. So 20, 25 are going to be the 2 that we are going to specify for new applications, and 14.5 is going to be for existing replacement parts. Remember that not only do gears have to have the same diametral pitch, they have to have the same pressure angle as well. So when you're specifying gears, you'll be specifying both. And then lastly, the number of teeth. The number of teeth is going to influence the velocity ratio. We've already talked about velocity ratio. Velocity ratio is letting us know the number of times that our smaller gear, or the pinion, is going to rotate to get the gear to rotate around once. Now, we looked at, forget what the equation is. The equation is 1019. Up at the top of page 274, so just the page ahead right here, okay? We have all of these options for calculating velocity ratio, okay? Velocity ratio is going to be unitless, as we had talked about last time. And depending on what we know about the set of gears that we're looking at, do we know the number of teeth of each? Then we can calculate velocity ratio. We can just count them up. We can divide the gear by the pinion. So pinion is always number 1 in this case, and number 2 is going to be your gear. We can get the physical size of the pitch diameter. That's what that small d is, pitch diameter. We can get the radius of that pitch diameter. That's what the r's are. Or we can get the rotational speed. Notice here that when we do the rotational speed, the pinion rotational speed is on top and the gear is on the bottom, because I like to think of it as my larger number always has to be on top. So physical size, or the number of teeth, our gear will always be larger. But when we talk about rotational speed, our pinion will always be larger. So be careful when you use these that you get the 1 or the 2 in the right spot, okay? We did add that to our equation sheet, so double check that again, that is where it's supposed to be. So it is going to directly affect the velocity ratio. And in general, the goal is to keep our design as compact as possible, meaning we don't necessarily just want to have one small gear for our pinion, super small, and then a really large one for our bigger one. We're going to talk about ways that we can reduce that and maybe even break it into multiple velocity ratios very soon after this section, okay? Now, the other thing we want to keep in mind is that our number of teeth has to be an integer number, meaning it has to be to a whole number. It doesn't have to be an even or an odd number necessarily, but we can't have a decimal of a tooth, meaning if you come out with number of teeth being 25.4, I can't have a 0.4 of a tooth. I can only have a whole tooth. Okay, so then you would either go up to 26 or go down to 25. Okay, would be the number of teeth on a given gear. Also, manufacturers do not stock or make all integers. So in the cases of the problems we're going to be doing for this class, we're going to be using the information from the book, the tables from the book. And we will see that for a given diametral pitch size, we don't make each and every integer number from, if you would, 1 to 120, okay? There are going to be gaps in the number of teeth on a gear that it's going to produce. So what that means is when we're specifying a set of gears, we have to make sure that both of them are in stock or available to be made by that manufacturer. So we'll usually have, in our case, we're going to have our catalog or our book open to the tables we're going to use. But in the case of if I'm buying it from a specific vendor, I have their catalog open. And now I'm going to be only specifying gears that are on their list of available in-stock gears, okay? So if we look at table 10.7 in your book, which starts on the bottom of page 276 and then goes to the next page, go down here, zoom out a little bit. This is table 10.7, okay? And what this has is it has sections in, as you'll see here. So the first section is a 32 diametral pitch. Then we've got 24, then we've got 20. And as we go to the next page, our numbers in the diametral pitch are going to get smaller and smaller. Again, down here at the bottom, our largest numbers of diametral pitch means these are the smallest teeth. And as we go to the smaller numbers, the teeth get larger in relationship, okay? Now, underneath each one of those diametral pitches are numbers that correspond with the number of teeth on a gear that would be made in that diametral pitch range. So for instance, if I look at the diametral pitch of 10 here, notice that they're saying they make 12, 14, 15, but look at, they didn't do 13 in between. So 13 would not be an option for calling out the number of teeth on a gear if we were looking at the diametral pitch of 10, okay? As we move over here, we've got 16, 18, 20, again, some more skips and so on. So when we're selecting gears that are in mesh with one another, number one, they have to be in the same diametral pitch section, and there has to be a partner with them. So if you specify 18, you cannot pick 23 for mating gear, okay? You have to pick something that's on the list here, and that's going to be what we look at, you know, a couple examples in doing, okay? And that's going to be, I think, two of the homework problems that you have are going to be specifying a set of gears, and you have to ensure that they're on the list, okay? So, so let me just catch up with our PowerPoint. I think we're ready to look at example 10.9, okay? Example 10.9, all we want to do is we want to determine what is the appropriate diametral pitch for the concrete mixer from example 10.3. So if we go underneath here, we have example 10.9, which is on page 276. We want to pick a pair of mild steel gears are to be selected for the concrete mixer that was described back in problem 10.3. We don't have to specify the number of teeth here. The only thing they're asking for is what is the appropriate diametral pitch when we have a 10 horsepower engine that is going to be supplying the power and the rotational speed at 1800 RPMs. So if we go back to that example, and we actually did that example, okay, they've already picked out the number of teeth for each. So we're not worried about selecting gears right here. We just want to know what is the appropriate size diametral pitch. So the gas-powered engine is right here. And off of that, the shaft is coming out, and on there is where that pinion gear is going to be mounted. That means that this is going at 1800 RPMs, and it is delivering, did it say 10 horsepower? I'm trying to remember, 10 horsepower to the cement mixer, okay? So in that case, as we can see here, the smaller gear, the pinion, is going to be rotating faster than what the larger gear is going to be, okay? So we are going to pick our diametral pitch based on the faster of the two. It's going to be the pinion, which is the pinion is always the smaller of the two in your mesh gears, okay? So that's the arrangement that we have. So using that information, 10 horsepower and 1800 RPM, we're going to go to table 10.6, okay? And all they want us to do is find out what is an appropriate place to start with your diametral pitch. So our power that we're delivering is 10 horsepower right here in this row. And we're going to go over where it lines up with 1800, which is right there. And it looks like, zoom in here a little bit, that is number 8. Okay. So that means that our diametral pitch that we are going to specify for this set of gears is going to be 8. Now, I also want to let you know that at this point in the layout of our gears, we're not going to be going back and changing this. We will find out if that diametral pitch is okay when we finish up the gear design. And that's something you're going to do in machine design elements. That's where, when you find out, okay, what are the forces that are generating? What are the stresses that you're going to be seeing? And you'll find out that there are 2 stresses that every gear is going to see, and that's going to be pitting stress on the surface and the bending stress of that tooth over or shearing off. Okay, so we have to resist that. So what you end up finding out in that process is what are the stresses that are generated, and then you compare those back to what are the stresses that it can actually take. And in some cases, if you find that the stresses are too high with this value, then you would go up a size or 2 on your diametral pitch, meaning you want it to be bigger teeth because you have stresses that are too high. So what I'm trying to say here is this is the place to start. So in kinematics, we're not worried about forces or stresses or those pitting stresses or those bending stresses. There's more to finishing up this design. Okay, that's my point here. And you will finish those up when you're in design of machine elements. Okay, so we'll be revisiting gears here. So for the answer to this question then, for example 10.9, it's actually very simple. All we're going to do is we're going to, and because you're going to be handing this example in, I know there's not much to this one, but example 10.9, okay, our diametral pitch is going to be equal to 8, okay, and that's from table 10.6, okay, and that's it. This is the answer to that question. The diametral pitch is equal to 8, and it's just reading it off of the chart by taking that 10 horsepower down that first column and then going across the row until we match with the 1800 RPMs, and it's just using the 8, okay? The next problem we're going to do gets a little bit more involved in terms of now we're going to pick the number of teeth on each of the gears for the application. So let's go ahead and look at example 10.10, which is the next example we're going to see here. And in this case, let's read what we have. So it says that we have a gear reducer is used on a concept for a small trolling motor for a fishing boat. The gears must transmit 5 horsepower from an electric motor that's going at 900 RPMs to a propeller down to 320 RPMs. So we're going to be picking a set of gears to go from the 900 RPMs, and it's going to finish up with 320 RPMs. We want to select a set of gears to accomplish this task, okay? So first things first, always first, we have to pick our diametral pitch, okay? Because we have to pick our diametral pitch because then it'll tell us what number of teeth on a gear do we have available. So they're telling us diametral pitch of 10. Okay, let's make sure that we can get that. So we know that we're transmitting 5 horsepower, and we know that the pinion is going to go at 900 RPMs. So for this problem, we're going to go back to table 10.6. We're going to go down to 5 horsepower, and we're going to go over to the column where it says 900 RPMs. And notice that, yes, indeed, the number is 10. So we're going to start there with this problem, okay? So for this problem, grab a new piece of paper. Or this example, I should say, yes, it's not an assigned problem. So for this example, so again, example 10.10, okay? Our diametral pitch is going to be equal to 10. And remember, this is teeth per inch, okay? Because we are going to be adding those units when we do our problem. And you can just say from table 10.6. I want to make sure that you know where you're getting that from because you will be having to specify it in your assigned problems, okay? Now, this means that our diametral pitch of 10, okay, we're going to go directly above here. In table 10.7, we are going to focus on this section right here where we have a diametral pitch of 10. Our gears are going to be picked from the number of teeth that are available. So the number of teeth on a diametral pitch of 10 here is going to be the numbers that we see here. So these are the only number of teeth that we can have on our pinion and on our gear. Okay, these are the ones that we have to pick from. And we have to hopefully be able to achieve that reduction from 900 RPMs to 320 RPMs, okay? So what we need to do first is let's figure out what our velocity ratio is going to be that we have to deal with, okay? So in our problem, it says that we have to go from 900 RPMs to 320. So if we go back to our equation sheet, the information that we have here is our starting and our ending angular velocities, or our W's. So we know both of these, right? We know both of these. So we're going to calculate our velocity ratio. It's going to be equal to our W1 divided by our W2. W1, remember, the ones are pinions, the twos are gears. So in this problem, it told us that our pinion is going to be rotating at 900 RPMs, and our gear is going to be rotating at 320 RPMs. Make sure you put your units in all phases of the problems. These cancel out. So what is the value of our velocity ratio? What do we get when we take 900 divided by 320? Everybody should have their calculator out and calculating it for me. We have a couple people in the chat. Awesome. 2.8125. Yep. Let's hold the decimal places. Yes. 2.8125. Okay, so 2.8125. Perfect. All right. And we want to hold a couple, especially when it's not to a whole number, because then we're going to be able to get closer to the actual size, the number of teeth. Okay. So now let's look back at our equation sheet. Okay. Now we know that our velocity ratio is also equal to the number of teeth in our gear over the number of teeth in our pinion. Okay, so gear and pinion. And we have the gear on top again because the number is going to be higher. So we can say that velocity ratio is equal to the number of teeth in our gear divided by the number of teeth in our pinion. Okay. Now I'm going to rearrange this because we are now going to solve this for the number of teeth in the gear. So if we get N2 by itself, go ahead and do the algebra to calculate or rearrange this equation to solve for N2. Okay. Go ahead and write down N2 equal to, what would it be equal to? Now N2 is on the right-hand side by itself. And to get rid of N1, I would multiply both sides by N1, right? So that means I would have N1 times the velocity ratio, okay? N1 times velocity, or putting in my number for the velocity ratio, I can say that N2 is equal to N1 times 2.8125, okay? All right, any questions so far? Now, we know that this ratio has to be maintained. So what we're going to do is we're going to look for values that are going to give us that exact number. So and this is just a trial and an error. Okay. Now that we know what we're going to multiply by, okay, we're going to then try N1 equal to, and we're going to go back up to our chart here, and we're going to look in this section. Okay. What do we want to start with? We can start with 12. We can start with 14. We can start with 15, 16, whichever number here. We're going to kind of start on the left-hand side here for the smaller. So let's start with 14, just to not be the smallest. So I'm going to try 14 teeth for my N1. Okay. So that means I'm now going to use this equation right here. And I'm going to say, okay, N2 is going to be equal to N1. Now N1 we said is going to be 14 teeth. So I'm going to put 14 teeth in here. And I'm going to multiply that by 2.8125. Okay, what does my N2 come out to be when I multiply those two together? 39.375 teeth, right? Teeth. Now, if we look on top, number one, we already know that there's not going to be 0.375 of a teeth, right? And if we look up here, that's where we start. Okay, I've got 14. Do I have a pair? I got 49, but this problem wants to go from 900 to 320. It's not giving us a range that we have to be in. It's saying we got to be at 320. So this is not going to work. This is not going to get it for us. Okay. So we try the next tooth. We can maybe try 15. We do that very same thing. So now we're going to try N1 equal to 15 teeth. Okay. So that means that N2 is going to be 15 teeth times 2.8125. Oops. What is our N2, our mating gear? How many teeth would it need? So 42 point what?
1875.
1875 teeth. Well, 0.1875 is not going to get us there, right? That's not an even number. And is 42 even a value? It is not. It goes from 40 to 45. So it wouldn't be an option for us. All right, then we're going to go to the next one. And this is literally how you do this. Now we're going to try 16. Okay. So I'm going to turn my page over here. And I'm going to do that very same thing. I'm going to say, okay, I'm going to try 16 teeth. Okay, for N1. So that means my N2 is going to be equal to 16 teeth times 2.8125, sorry. 8125. And what do we get for N2? Everybody should be multiplying this out. Have your calculator out. I shouldn't be seeing anybody waiting for everybody else to calculate it for you, please. It's more fun when it's interactive. Emily got 45. Did anybody else get 45, an even number? Okay, awesome. So that's a possibility as long as it's on our chart. So let's look. If we look up here, 10, oh, there it is. So that means that this pair going from 16 teeth to 45 teeth is going to get us that required velocity ratio of 2.8125. So that means it's gonna work for us. So that would mean that a viable option would be our N1 is equal to 16 teeth. Our N2 is going to be equal to 45 teeth. Okay, so this would be a set at a diametral pitch of 10. Okay. Notice that if we go to a diametral pitch of 8, they have a 16, but they don't have a 45. So this only works for a diametral pitch of 10 right now, okay? Now, there might be some other options in there, and if you were like, I do 16, I want to do something else, you could then continue to try different numbers with that pinion, okay? But this would be a viable option. So diametral pitch is going to be 10, and the number of teeth here is going to be 16. So when you do your problem, make sure that you have, oopsie, should have a box around diametral pitch of 10, and then a box around, because our final answer is going to be the number of teeth in our pinion, which is number 1, and the number of teeth in our gear is going to be 2. You have to do more than one iteration. All right, you have to show me a couple iterations here, meaning ones that don't work until you get something that works. Make sense? All right. All right. So that's going to be selecting gears. And again, using gears that are available to us, in this case from the chart in the book, but otherwise you would have a vendor catalog open letting you know what they have available. So that means that this takes us to the end of this PowerPoint, okay? We're going to be moving on now to looking at gear trains, okay? Gear trains. And that's going to be part of the second PowerPoint presentation that we have. So I think what I'm going to do here, this probably is a good place to stop this recording, and then I'm going to start the new recording with